ever stop to think about what makes a machine work? And maybe more importantly, what makes it just stop? Whether we're talking about a simple hand tool or a massive, complex production line, failure is something we all have to deal with. So today, we're going to get into why machines fail and, crucially, what we can actually do to stop it.
It seems like such a simple question, right? Why do things break? But the answer is anything but simple. Really, getting to the heart of why things break is the absolute first step to preventing it. It's all about changing how we think, moving from just reacting to problems to actually getting out ahead of them before they can even start.
And you've got to understand, the stakes here are incredibly high. A single machine going down can bring an entire production line to a grinding halt, and that means huge financial losses. But even more important than that, an unexpected breakdown can create some seriously dangerous situations for the people working on the floor.
Okay, so here's our game plan. First, we'll look at the usual suspects behind breakdowns. Then, we'll do a deep dive into the anatomy of a failure itself. After that, we'll learn how to hunt down the real root cause, build a solid prevention playbook, and finally, we're going to explore what happens when the problem isn't a part, but the entire system.
All right, let's jump right in. Why do things break? We're about to uncover some of the most common culprits, and I think you'll be surprised at how often it comes back to people, not just parts.
So when you really boil it down, breakdowns usually fall into 5 main buckets. You've got improper operation, that's often just a lack of training. Then, of course, there's poor maintenance, pushing machines way past their limits as they get older. You've also got people straight up ignoring clear warning signs. And the big one, a company culture that just doesn't make reliability a priority.
Okay, so now that we've seen the common causes, let's get our magnifying glass out and look at the anatomy of a failure. By really studying the wreckage, we can start to understand the physical forces that actually lead to a break. A really key idea here is what's called the failure mode. Now, this isn't just about saying something is broken. It's about how it broke. Was it a sudden snap? Did it slowly wear out from fatigue? Or did corrosion creep in and eat it away? Each one of those modes tells a completely different story.
And this slide shows 2 of those stories perfectly. Over on the left, you've got a ductile fracture. Think of a material like steel. It actually stretches and bends. You can see it deforming before it fails. It gives you a warning. But on the right, a brittle fracture gives you no warning at all. It just snaps, suddenly, catastrophically.
And then you have fatigued. The paperclip analogy is perfect for this. You know how you can bend a paperclip back and forth? It seems fine on the first, second, third bend. But each one of those cycles is creating these tiny, invisible cracks that just keep growing until, snap, it fails. That is exactly what happens to machine parts under repeated stress, even if that stress is technically within its limits.
And we absolutely cannot forget about corrosion. It's like the silent killer of machinery. It's way more than just rust. You've got galvanic corrosion, which happens when 2 different metals start reacting with each other. There's pitting, which creates these deep, nasty little holes. And then there's stress corrosion cracking, which is a truly deadly combination of a part under stress in a corrosive environment. So all of this brings us to what I like to call forensic engineering. This is where we put on our detective hats. See, it's not good enough to just know what broke. We have to figure out why it broke in the first place. And the main tool in our detective kit is root cause analysis, or RCA. It's basically a step-by-step process for digging past the obvious symptoms to find the real origin of the problem. And the goal here is huge. It's not just to fix the broken part, it's to make sure this never happens again. One of the most powerful and simple RCA methods is called the 5 whys. It's so elegant. You just keep asking why until you can't anymore. So the machine stopped. Why? Well, the fuse blew. Okay, why? The circuit overloaded. Why? The bearing seized up. Why? Because it wasn't lubricated. And boom, there it is. In just 5 simple questions, you went from a surface-level symptom all the way down to the real root cause. But let's be real, failures aren't always that straightforward. As you can see in this diagram, sometimes human error is a whole complex web of different things. Experts will actually map out everything from poor training and bad information to just plain old carelessness to get a full picture of how one single mistake was even possible. So everything we've talked about so far has been about looking at failures after they happen. But the real win, the real goal, is to get ahead of them. So this next part is all about the prevention playbook, the strategies that let us be proactive instead of just reactive. And the big tool in this playbook is FMEA,
which stands for Failure Mode and Effects Analysis. This is a totally proactive process. You sit down with the design, you look at every single component, and you ask two simple questions. How could this part possibly break? And, okay, if it does break, what happens next? It's an incredibly powerful way to find and fix problems before they ever see the light of day.
And this quote here really sums it up perfectly. The whole point of FMEA is to identify and get rid of potential failures while they're still on the drawing board, long before they have a chance to cause a real-world breakdown.
But here's the thing, and this is absolutely crucial. All the tools and analysis in the world aren't enough on their own. The ultimate solution, the real game changer, is building a strong reliability culture. A culture where every single person, from the C-suite down to the frontline operator, feels a sense of ownership for preventing failures. Okay, for our final section, we're going to zoom way out and tackle a much deeper, more complex idea. What happens when it's not just a single part that fails, but the entire system itself? And this leads us to a really challenging concept from a sociologist named Charles Perrow. It's called the normal accident hypothesis. What he argued was that in super complex, tightly connected systems, think nuclear power plants or air traffic control, some accidents aren't just possible. He said they're pretty much inevitable.
Now, to really get this, you have to compare two different ways of thinking. On one hand, you have the traditional reductionist approach, where you just analyze each part by itself. But then there's the systemic approach. This way of thinking recognizes that the complex interactions between all the parts can create totally unexpected behaviors, things that you'd never see by looking at the parts alone.
And that, right there, is the core idea of a systemic failure. It's a breakdown that happens even when every single component is working exactly the way it was designed to. The failure isn't in any of the parts. It actually emerges from the mind-boggling complexity of the whole system working together.
Which leaves us with one last big, provocative question. Can we actually engineer systems that are perfect, that are truly immune to failure? Or, as our world gets more and more complex, do we just have to accept that some accidents are normal? It's definitely something to think about. Thanks for joining us here on NextGen Manufacturing Nexus.